Hi, this is Guillermo Campitelli, and this is the last video of the series of videos for the model comparison approach. In this case, I'm going to explain the Bayesian approach to model comparison, which uses Bayes factors. Okay, so when we compare the Bayes factor approach with the maximum likelihood approach that I explained in the previous video, I already explained that the maximum likelihood approach compares the likelihood of two models. Now the Bayes factor is in this respect is very similar because it compares what we call the marginal likelihood of two models. So it does it in a different way, but the idea is how likely is one model, how likely is another model, and we make the comparison of the likelihoods. Now the way the likelihoods are calculated is different in the two approaches. Okay, so in the maximum likelihood approach, only one parameter value is used to calculate the likelihood of an observed value. As I explained in the previous video, we use, let's say, a normal distribution, and we, let's say in this case the predicted value is 0, and we determine what was the probability of, let's say we observe the score 3, so what's the likelihood or the probability of the value 3 when we are predicting the predicted value is m equals 0. The Bayes factor, we don't do that. We, instead of using one value of the parameter of interest, we used all possible parameter values, because remember that the first step of the Bayes approach, the Bayesian approach, is to assign a prior distribution to possible parameter values. So instead of saying, okay, this is the best parameter value and let's see how good that model is, the model assigns a prior distribution. So the model says, well, I believe that this parameter value is the most likely, other parameters value are a bit less likely, and so on and so forth. So we've got a probability for each parameter value. So that means that we cannot use just the best parameter value to make our to calculate the likelihood of the model. We have to use all the possible values, and those values are going to be weighted by the probability that we assign with the prior. So here I illustrate, this is the figure that I used in the parameter estimation approach, the Bayesian parameter estimation approach. So basically, instead of using one distribution as to calculate the likelihood, we are going to use, in this case there are 11, but remember that this was a bit of a cheating. This should be infinite number of distributions, and so we are going to use the combination of all these distributions to determine if a value observed is what's the likelihood of observing one specific value. So that's the main difference between the maximum likelihood and the Bayes factor approach. Okay, so priors. The first thing we are going to do is to assign prior probabilities to the parameter values. Now we are going to use the software JASP to run the analysis, and I'm going to show you briefly how are we going to use this software. And so we need to assign a prior to all the beta parameters, but JASP uses mean center values. So instead of using the raw scores of the variables, it transforms them into mean-centered. So basically the mean of those scores will always be 0, and there will be values that will be negative because they are lower values than the mean, and there will be positive values because they are higher values than the mean. Now, by doing that, beta 0 is not necessary, because it's there is no need for that parameter. So all the other betas, then we need to assign a prior distribution. So there is a default distribution with a default parameter in JASP, which is the Cauchy distribution, and the Cauchy distribution is in a sense similar to the beta. So sometimes a normal distribution is used, but the authors of JASP, in fact, JASP runs in the background a package of the R software. That package is called a base factor, and so the author of the package decided to use as default parameter this one. Now I'm going to explain what that means. So basically, here in this graph we have a representation of different Cauchy distributions. So this one with the salmon color is a Cauchy distribution with this R value 0.1. So you can see that the values they are more likely when they are close to 0, and very quickly values that are further away from 0 become very, very unlikely. So then we have this distribution, which is the Cauchy .345. So that's the actual default distribution, prior distribution that uses JASP. So you can see that values are close to 0 or 0 are the most likely, but it's not as likely as in a Cauchy with the 0.1. And and values that are -1, they still have some likelihood, not that close to 0. Okay, so that's the default. There is no, if we don't have any other expert knowledge, we should keep it that way. But in some circumstances, we may want to change it, and we can change that our scale parameter. So the green one here is a Cauchy with scale parameter 1, and the blue is a Cauchy with a scale parameter 2. Now I also plotted a normal distribution, which is this pink one, to show you the differences and similarities. So that's a normal distribution with mean of 0 and standard deviation equals 1. So as you can see, it has the same characteristic of the normal in terms of symmetry, and it's around what is called the location parameter, and here the location parameter is set to 0, so the distribution is around the value 0. Okay, so this is the prior distribution for the betas. That means that the beta 1 or beta 2, depending on which model, and the model says, well, I think that the most likely values are between 0 or close to 0. You have to take into account that because the values are mean-centered, then they don't have the same interpretation as the beta values that I have been using, which are not mean-centered. So basically, there is an easy transformation of betas to unstandardized betas, and so the calculation is easier this way, but I prefer to keep the betas unstandardized because they are more easy to understand. Okay, so these are the priors, and then so that's the as mentioned in previous videos, this is the unique aspect of Bayesian statistics. We assign priors to possible parameter values. Okay, so for the probability of the data, this is similar to the maximum likelihood. So we are going to use a normal distribution with a mean of mu, which is the predicted value, and that's the same. So once the beta 0, well, beta 0 is not estimated, but once the beta 1, beta 2, beta 3, depending on the model, is estimated, then the formula that we use to come up with a mu is the same as in the maximum likelihood approach. So we are going to get a mu. So given that mu, what's the probability of observing specific value of mean of academic achievement? And because academic achievement is mean centered, we use in order to establish the likelihood of a score, we are going to use a mean of 0. So standard is a normal distribution with mean of 0 and standard deviation 1, and we are going to determine what's the likelihood of that. But remember that we are going to calculate it for each. So we are going to, instead of calculating the likelihood of a score given a mu value, we are going to have infinite number of mu's, because the mu's will be calculated with the betas. And as I told you before, betas will have a prior distribution over possible values. So we are not going to use only just one beta, we're going to use all the possible betas, and some of betas we are saying they are more plausible than others, but those betas will give a mu, and then with those mu's we use this distribution to determine how likely is to obtain the observed score. So it's quite complex. Obviously we are not going to do that. That is not possible to be done, so we are going to approximate that, and actually we don't do the approximation either, we let the software do that for us. Okay, then what we said before is that we are going to calculate the marginal likelihood of two models, and we are going to compare the marginal likelihood. Now, because when there is more than one parameter, calculating the marginal likelihood is almost impossible. In almost all the cases, it's impossible. Sometimes there are ways of calculating it. So we need some sort of simulation, such as Markov chain Monte Carlo, to approximate the marginal likelihood. And in fact, JASP does not provide the marginal likelihood. It provides directly the base factor and also other pieces of information that I'm going to show. Okay, so I think this is a good time to show you JASP. Okay, so this is the website in which you can download JASP for free. JASP is a software. The reason why I chose this software is because it's free, one of the main reasons. The other one is because it allows calculation of a lot of Bayesian analysis in a very, very easy way. So the disadvantage of using JASP is that there are some analyses that JASP cannot do, but it is a very good introduction to Bayesian statistics. So I'm going to show you, I'm going to use JASP and for these reasons. It's free, it allows Bayesian statistics, and is very easy to use. So this is the website where you can download a JASP, and let's see if we've got the people who develop. Is the University of Amsterdam. Eric Jan Wagenmakers is obtained a grant to develop this software. So let me see. Okay, here it is. I found the JASP team. Yeah, Eric Jan Wagenmakers is the main guy under JASP. He wants to popularize Bayesian statistics in psychology. He is a psychologist, and he developed this software. He's not the actual IT guy developing it, but he is the one who leads this team. So it's important to mention them because they offer this fantastic software for free. And JASP doesn't work from, it's not a project that starts from scratch. It uses the R software, but especially a package called Bayes Factor developed by Richard Murray, and again he's a psychologist. So these are two psychologists who are doing statistics things, and that's because they understand the problems that psychologists have with statistics, and they want to provide software to do analysis in a simple way. So behind JASP is Bayes Factor is working and using the R software that I'm going to show you another time. Okay, so let's go to JASP. That is how it looks like. Now, the first thing you have to do is to open a file. Now, a file would be a file, an Excel file, but actually should be saved as an CSV file. So I'm going to browse. I'm going to go to chapter 6 sample, and if you can see, is a comma separated value file, so it's a CSV file. So basically you go to Excel, and instead of saving it as a normal file, you save it as a CSV file, and we open the file. So here we have the file. The file has a lot of variables, but we are interested in 4 variables only. But you can see there are 300 observations, and it's a typical Excel file. So now you can see everything. Okay, so we have this file, and then we have a lot of modules that which we can do analysis with, and in this case we are going to use the regression one. And in the regression one, you've got here, these are the traditional analysis, and these are equivalent Bayesian analysis. So for this one, we are going to use the Bayesian linear regression. The dependent variable is academic achievement. So very simple. We select and we pass it there, and then the covariates are teaching quality, study hours. I'm putting study hours first, teaching quality, and as you can see, it's doing things even without me doing anything. So it's so good, this software. Now, knowledge is the other variable. Now, let me show you everything. Okay, so here we've got Bayes factor 1, 0. We can invert the Bayes factor to obtain the 0, 1, or we can obtain in a logarithmic scale. We are not going to do that. We can compare to the null model, or we can compare to the best model. We're going to keep it a comparison to the null model. Then we've got the model. We can change the null model, and I'm going to explain this later. And in advanced options, we can change the priors. So I showed you before. So I told you before that the prior parameter is set to 0.354, but we can change it if we have reasons to do so. And basically, that's it, because it did the analysis already. I show you the analysis output here. We've got models. Now here there are 8 models. We are not interested in all of them. We are interested in null, which is our model 0, in study hours, which is our model 1, teaching quality, our model 2, study hours plus teaching quality is our model 3, and knowledge is our model 4. So these 3 models we are not interested in. There is no way I can get rid of them without having these models. But it doesn't affect what we are in the calculation of the base factors. Okay, so this column PM is the prior probability of each model, and here JASP has only one option, which is to assign the same probability to each model. So basically we've got 8 models. The probability has to add to 1. So we do 1 divided by 8, which is 0.125, and that's the probability, the prior probability of each model. So basically we are saying that before analyzing the data, we think that each model has equal plausibility. Sometimes we want to change that. JASP at the moment doesn't allow to do that, because sometimes we know that one model had more empirical support than another model, so we want to give them a higher prior than the other model. But typically we don't do that. We keep the same prior to the models. So until now I was talking about assigning prior probabilities to parameter values, but this is another aspect that is important. We can assign probabilities to anything, so why not to assign it to models when we are doing model comparison? So this is why we've got this. Now, probability of model given the data is the posterior distribution. So we've got the prior distribution of the model and the posterior distribution of the model, and again this will add up to 1. So you can see that study hours plus teaching quality is our model 3, went from 0.125 before seeing the data to 0.509 after seeing the data. So this is the most plausible model after seeing the data. And knowledge is our model 4, is also relatively good because it went from 0.125 to 0.352. All the other models went down, as you can see here. And these are in scientific notation. You can see very small values, because E minus 54 means that it will have like 0.0, like 53 zeros, and then 1531. Minus 6 is going to have 0.5 zeros, 1011, and so on and so forth. So these 3 models are very, very low plausibility. Most of the plausibility is captured by the other, these 2, and a bit the other models. Now, that's not what we are interested in. So the posterior distribution of the model gives us a good information, but because we have these models that we are not interested in, it's not very accurate. So, but what we are interested in is this column, BF10. Now, I explain what BFM is. BFM is actually how much the model improved after seeing the data. So basically it's the ratio between probability of the posterior probability of the model and the prior probability of the model. So this divided by this equals BFN. This divided by this is here. This divided by this is there. This divided by this is there. So basically we can see that the model 3 is 7.2 times more likely than it was before seeing the data, and model 0.4 is 3.8 times more likely than seeing the data, and all the other models are less than 1, so basically they are less likely than before seeing the data. But the most important Bayes factor that I'm interested in is the this column BF10, which is the comparison between two models. The model that is in this row, in each row, sorry, versus the null model. Yes, so basically, obviously, the null versus the null is 1, but then the others are, this is the Bayes factor. So basically, all the models are better than the null by far. Okay, so now this gives us comparisons against the null model. So we can do model 1 versus model 0, model 2 versus model 0, model 3 versus model 0, and model 4 versus model 0. Model 0 is the null model. But how do we calculate the Bayes factor between, let's say, model 2 and model 1? Well, it's easy. We calculate the ratio of the Bayes factor. So we don't have that value, but we can calculate it indirectly. So basically, this is model 2 and this is model 1. So basically, the ratio of these two gives us the Bayes factor 2:1. So the Bayes factor is how much more likely is model 2 versus model 1. Okay, so the other way of obtaining it is to change the null, and I told you that you can do it here. So basically, in this option, you can add variables to the null model. So let's say I want to add study hours to the null model. So that changes the models, because now the null model include study hours because I indicated that. So now when we calculate this column Bayes factor 10 is all the other models versus this one, which includes study hours. Yes, so that's another way of obtaining a Bayes factor, but we cannot obtain all of them by doing this method. So the other option is, as I said before, we take the Bayes factors in this, and we obtain the ratio of these Bayes factors. I'm going to explain with the slide as well. Now, one thing that I wanted to show you is that when we added a variable here, the PM varied, because now we have 4 models and we have to distribute the probability of 1 between 4 models. So now the prior probability of the model is 0.250. So that doesn't affect the calculation of the Bayes factors. Just wanted to tell you that it changes these, it changes other things, but not the Bayes factor. Okay, so let me return to the slides. Okay, so basically that's what I explained. When we want to calculate, so JASP gives us Bayes factor 10, so model 1 versus model 0, Bayes factor 2, 0, so model 2 versus the null, but it doesn't give us Bayes factor 1, 2. So basically we just obtain the ratio of these two factors and then we obtain the base factor 1, 2. And the other option is to change the null model in JASP. Any of the two will work. I prefer this one, so you don't have to do any extra in JASP. You can just use a calculator to obtain this ratio. Okay, so once we do all these, then these are the base factors. So base factor 1, 0, 2, 0. So all the comparisons against 0 show very high values, and I show you here base factor 2, 1 is the same as base factor 2, 0 divided by base factor 1, 0. In the others I'm not showing, but we did this calculation as well. Now we sometimes when we get the value of the base factor that is less than 1, like in this case, return. So BF for 3, the base factor for 3 is 0.714. Then it's a bit of a mouthful to do the interpretation. So, for example, base factor 3, 1, we say model 3 or the data is 487,436 times more likely under model 3 than under model 1. In BF for 1, we can say that the data is 348,168 times more likely under model 4 than under model 1. And let's say BF20, the data is 288,566 times more likely under model 2 than under model 0. But this one is a bit of, we have a bit of difficulty to say what it is. It should be the data is 0.714 times as likely under model 4 than under model 3. Easier is what we can do is to invert this. So we calculate the base factor 3, 4, and we can calculate it in by doing base factor 3 first and base factor 4 late, then after that, and then we do base factor 3 divided by base factor 4. But the other way we can do it is we do 1 divided by this, and that gives us base factor 3, 4. So what I'm going to show you next is for all these base factors, I did 1 divided by each of those, and we obtain the inverse. So base factor 0, 0, 1 instead of 1, 0, 0, 2 instead of 2, 0, and so on and so forth. So now, instead of having base factor 4, 3 being 0.7 something, then we have base factor 3, 4, which is 1.4. So we can say that the data is 1.4 times more likely under model 3 than under model 4. Much easier to say than when it's less than 1. Okay, I think that finalizes the base factor approach. The base factor is much more complicated to calculate than the other approaches, but that's why I chose JASP, which is a very easy to use software. Again, the disadvantage of that is that JASP cannot do everything, but it can do a lot, and so as an introduction is really good to use this software.